Hello? All right, I think we're going to start. Thank you all for coming. I'm really glad everyone could make it, and I'm really shocked at all the interest in this group so far. I'm going to go through a few things to start with, kind of welcome you guys, tell you about what I foresee this group being about, and mention a few other things, and then we'll go straight into talks after that. So ideally, I want to make this the go-to resource for everything AI related in Northeast Ohio. Our mission would be to support the understanding and adoption of artificially intelligent systems by organizations and institutions in the Northeast Ohio region. And primarily we'll do this by providing an open access educational resource for aspiring data science, machine learning, and AI professionals and enthusiasts in the area. We'll also be exploring other opportunities to support this mission as the group matures. Meeting content will include a combination of surveys, project showcases, research walkthroughs, coding events. Creative ideas for other types of content are really encouraged, and if you have any ideas, please let me know. Preference will be shown to content that's accessible to newcomers, but rigorous enough to provide value for a wide audience. Due to the technical nature of AI, some content will be best suited for a more experienced audience, but those talks will be clearly designated as such. And then for the first few meetings, we're going to try to focus on introductory material. So with the exception of one talk in January. But if you'd like to speak, please contact me directly until we establish a more formal process for that. And like I said before, we want things to be accessible to newcomers, but also rigorous. And if you have a topic you'd like to hear more about, you can post it on our meetup page. See if anyone else would be willing to give the talk, or better yet, just do some research and develop the talk yourself. And I'd love to help anyone who's interested in doing that complete that. So special thanks to our sponsors tonight, Jumpstart, who provided the space, obviously. Giorgio's Pizza for providing that delicious pizza. And Pandata for sponsoring in other ways. If you're interested in what we do, come talk to Cal and Ian or myself. We'd love to talk. And we're always looking for other sponsors to provide pizza and meeting space. And if you have anyone in mind, please contact me directly. So this is kind of modeled after the Cleveland Big Data Meetup, what they do. At the beginning, we'd like to have a time for recruiters. If there's anybody who's offering positions or looking to fill a position, they can stand up, give a quick spiel, and see if anyone's interested. So if anyone has anything. Okay.
It's not a recruiter, but it's a volunteer shuttle.
Sure, yeah, go ahead.
Right. So this is driven by Microsoft Philanthropy and Microsoft. It's called CAIG. It's like a volunteer job to teach high school students for computer science. They're starting their computer science. So what they do is, I'm actually a volunteer myself. We spend about 2 to 3 hours a week going to high school in a field area. So usually it's the first hour the day, so you're done with it. And you're not the main teachers. You're actually helping Anyone wants to help? I have some flyers, and also I have the main person who runs this program. What language? They have like 2 or 3 curriculums. So, for example, they have one called Code.org. They go and set up some very basic program. We're talking like binary numbers, very basic stuff. They also have a Java programming class, but for the most part, for example, the class I go to, they learn something called Alice, which is basically graphics. Just pull a graphics and learn.
Thanks. Anyone else have anything? Okay. Up on the screen, we have some recent events. I'm sure you've all had a chance to look through that stuff. Upcoming events, there's a few. The Cleveland Medical Hackathon is coming up next weekend. Also, the Machine Learning and Data Science Meetup in Cleveland, where people get together and practice Kaggle competitions. That's going on the same weekend. So definitely suggest you go try to hit at least one of those. The Cleveland R user group is going to be hosting another meetup on October 25th. And after that, Chug's going to have a meetup in November, so which is the big data meetup. So hope you all enjoy those. They're great. So I think we'll start with talks now. First up is Billy Barbaro, and he's going to be introducing us to AI.
Can we get speaker notes up here, or is this because I don't have any speaker notes?
No, I think you do have notes.
Yeah.
I don't know how to do that though.
I don't know either. Usually they just like slow up, you know?
The laser pointer there. You want to use that?
Oh, perfect.
Yeah,
Great. Okay. We'll see what happens without notes. I'll have to exit out and look at the notes, and we'll take a look at that. So before I get going here, let's just give a quick round of applause to Jason for setting this whole thing up and getting it together. All the hard work involved there. Thank you, Jason. As he said, my name is Billy Barbaro. I'm a master's student down the road at Case Western University, studying in a machine learning lab there. So Jason asked me to give this talk tonight to kind of, I guess, kick off the meetup. So what we're going to do here is, I guess, kind of set the stage for other talks and things to come. So like anybody else who wants to know about something, before I started this talk, what did I do? I Googled it. So artificial intelligence. And I got some really interesting articles that came up here. Google AI defeats Go champion. AI learns to bluff and beat humans at poker. Self-taught AI beats doctors at predicting heart attacks. Deep learning does as well as dermatologists. I even got this strange one where AI beat humans in vision, apparently, and healthcare. So all like really exciting things. And the goal here tonight isn't necessarily to teach you how to make an AI, of my talk at least, isn't to teach you how to make an AI algorithm that you could take down to Jack Casino and beat somebody with poker. Although I'd be interested in that one for next time, if anybody's got any ideas. But it's to really provide kind of a high-level overview of the field. And like I said, set the stage for talks tonight and for meetups to come. So just one note, if you have any questions at any time, feel free to stick a hand up and interrupt, even if you just have an interesting insight. If we run short on time now, I might ask you to just come see me afterward, because yeah, we'll just go with that. All right, so an overview of the talk. First, we're going to go ahead and just define artificial intelligence, look at a little more about the field, and then we'll kind of step through the natural progression. We'll start in the past, move to the present, and look at some of kind of the current research areas there, and then do a little bit of a deep dive on machine learning, just because one, that's what I'm most familiar with, and two, I think that'll be kind of one of the better things to cover for the later talks. And then we'll spend a little bit of time at the end talking about the future. So let's get going with this. What is artificial intelligence? And when you look at this, I kind of turned back to the definition given by one of the founders of the field, John McCarthy. And most places, I guess, point back the field's roots to 1956, McCarthy, shown up there, was an associate professor at Dartmouth University. And prior to that, there had been all this research in like intelligent systems and other things like trying to model like intelligence, take like biological intelligence and model that in a machine. But nobody really brought it together until this 1956 summer conference by McCarthy. And when I say conference, he got together himself and 9 other guys. I think Claude Shannon was in there and a couple other notable ones, and kind of locked themselves in conference rooms over the summer at Dartmouth and kind of hashed out the field and brought the research area together. So when you look at how he defined artificial intelligence, he says this: it's the science and engineering of making intelligent machines, especially intelligent computer programs. So great. Artificial intelligence is bestowing intelligence or getting intelligence out of something that's, well, artificial. So what is intelligence? But luckily, he answered that question as well. And he said intelligence is the computational part of the ability to achieve goals in the world. And there's actually one definition I like a little bit better than this, which is intelligence is a capability that enables rational, flexible, and adaptive problem-solving behavior. So we can kind of break apart that triad there: rational, flexible, adaptive. Rational being, given information, it's able to draw a reasonable conclusion, a logical conclusion. Flexible being, it's able to do new things. So it's not just memorizing like what it's seen, it's able to go ahead and draw new conclusions from that, able to infer things. And then adaptive being these algorithms, the things in this field, can be applied to like a wide range of problems, depending on the data they're given. And as they get more data, more information, they're going to adapt to those. So real quick, just a couple of the really early things in the field. You have the problem of search. Which is basically, for those of you who aren't as familiar on the computer science side, it's like, okay, I have a start and an end, and I'm trying to get through the maze to the end. Other problems that were solved, logic. So you could think of this as like, if you've ever done philosophy, like first order, logic, resolution, things like that. In addition to, there's a class of problems called like satisfiability. So you know, like Booleans, you can have a Boolean expression like A and B and C, or B and C and not A, and so on. And then is there a possible assignment of those variables to satisfy that problem, to make it true? Other problems like optimization, so given a set of constraints, and then also like an objective function, so some function that I would minimize or maximize. How can I find the best value there? And then probability. I don't know how many of you are familiar with like Bayes' theorems and Bayesian networks, but that kind of draws back to the roots of the field as it was getting going. And again, all these things really still a big part, I think, of solving problems in the field of AI, but really the research into methods of search, methods of logic, aren't so much considered part of the field. And one thing I found really interesting as I was kind of writing this talk was this concept called the AI effect. I don't know how familiar everybody is with that, or with this, but that's basically saying that once a problem's been solved, it's no longer considered artificial intelligence. A lot of people give chess as an example. It's like chess used to be the gold standard kind of in AI many years ago. So can you have a computer beat a human at chess? You look back to like Deep Blue versus Kasparov. And then once it happened, it kind of faded out as AI. People were like, oh, you're just kind of like brute forcing through all the possible scenarios and trying to figure out what's there. And it's not as much considered on the forefront of AI anymore. So this is, on one hand, like kind of nice because it's pushing the field forward, right? It's never good enough. We're still trying to develop more and more as we move on. But on the other side, it can be kind of detrimental in a certain way. And one of the big things there is the problems that we're looking at with AI. So everybody looks forward to like these far off problems of like Skynet taking over the world or something like that. And there's real problems now with things being developed. So being able to use an AI to manipulate like a virus so it makes it pass like a malware detection system. Different things like that. So I don't know, just kind of like an interesting find. And that's all I have so much on the past for the history. If you're interested in more, by all means, like Google around. McCarthy has a website that's hosted by Stanford with like a really interesting kind of FAQ style on the history and background around it. And then also Stuart Russell and Peter Norvig have a textbook whose name I had in my notes, which I don't have in front of me, Modern Approach to Artificial Intelligence, I think. So that has a very nice history section and also goes into a lot more detail on some of those subfields that I just kind of flashed up there and ran through. But with that, kind of brings us into the present, which according to the AI effect won't be considered AI in like 15 or 20 years, but it is today. So we'll talk about that a little bit. What I want to kind of do is go through, I think, 4 or 5 of kind of the bigger research areas that are considered artificial intelligence today. And then we'll kind of do a deeper dive on machine learning, like I said earlier. So first off, computer vision. These are problems, all things to do with like image and video recognition. So you can think of something from, all right, I have a stack of images. Is this a cat or is it not a cat? You could think of something with video, so I have a bunch of faces. Can I track the faces through the frames of video? Even things like self-driving cars rely heavily on CV. Can I tell what's around me, see what's around me? And a lot of these problems are approached nowadays with like neural networks and deep learning. And if you're interested in more information, let me know, but we're not gonna go into any further detail in the intro. Next up is all things speech. So speech recognition and then NLP, natural language processing. Most prominently, you probably see this in our, well, I guess most of the time, smart assistants. Your Siri, your Google, things like that. Your Siri, your Google Assistant, I guess, stuff like that. So you have the problem, one, of when I say something, can the computer understand what I'm saying, which is kind of the speech recognition part of it. And then once I get those words, can I somehow unearth the meaning behind those words to figure out what the person meant? And then you also have the flip side of, I'm a computer and I want to convey something. So how do I do, it's called NLG, natural language generation, where how do I say something back to the person? How do I encode this data that I have into human speech? Chatbots are another interesting like application of this that you see without, I guess without the vocal part of it going on. And that kind of brings us to another big problem in the field, or another thing a lot of people look at, which is knowledge representation and reasoning. Knowledge representation gets into this whole idea of, okay, I have this human, I have something, I have this idea, this concept. How do I encode that so that the computer can understand it? Because I can't really learn or do anything without having that information. So as humans, we have the world around us, we have text, which we can read and things like that. As the computer, we have to find a way to encode that for them. So something like an image, something that's visual for a computer, that's pretty decided upon how we're going to represent that, right? You have a picture with the pixels. Each of the pixels has a red, a green, and a blue value. And you kind of go from there. But then when you move to something like language, that gets a little more difficult. So now really, like when we say a word, when we say something like table, that's really more than a table, right? So how do you convey to a computer, how do you represent the fact that like, when I say the word table, I'm referring to this concept, this something in the real world, and kind of ground that, that word. And we'll get into representation also for like a lot of the machine learning stuff later with an example. And then the final one I just kind of wanted to highlight was robotics. This is a GIF of a robot that I found particularly interesting. I don't know, it loops well. But so this is really a combination of some of those fields. And these are all subfields and they're so overlapping. So when you have a robot, you have to have computer vision. You need to be able to do like something called planning, which is like trying to figure out how to accomplish a goal. If you want your robot to speak, then that whole natural language thing comes in. And then I also think it's really interesting because we kind of set the standard for intelligence as ourselves, being self-centered human beings. So in order to kind of accomplish something that lives up to our standard, it needs to be embodied and physically embodied. And robotics kind of accomplishes that. And has led to some really big advancements in the research. So with that, that brings me to machine learning. We're going to take a little bit deeper dive into things. So I want to break that up into really 3 major kind of subfields: supervised learning, unsupervised learning, and reinforcement learning. So we'll kind of go over each of these briefly here. And then I came up with a little example with like songs to demonstrate a problem you could solve with each of these. And then we'll go through those individually. So supervised learning. This is learning from an expert, learning from somebody else. So you can have a situation in which I'm given a bunch of pictures of food. And each picture is labeled as being a hot dog or not being a hot dog. So once you have those pictures, I can look through them and figure out, okay, like get a pretty good sense of what a hot dog looks like. And then somebody gives me more pictures, and now it's up to me to label those as hot dog or not a hot dog. So that's supervised learning, learning from an expert, learning from labels. Next up, we have unsupervised learning, which comprises a decent amount less. So as you can see, supervised learning is like what the field is primarily focused on now. Unsupervised learning is learning from observation. So you don't have the help of somebody else. I just give you a bunch of stuff. Let's say you gave me like a bag of rocks, and I'm not a geologist by any means, but I could go through those rocks and feel them for grittiness and how heavy they were and their color, and kind of put them into a few separate piles. And I might not be able to tell you like that all the rocks in this pile are like sedimentary rocks, but I could tell you that they were all similar in some way. So that's unsupervised learning, kind of learning just to group things together, to cluster them, learning similarity a lot of the time. And then finally, reinforcement learning. And this is learning from exploration. So, and the rewards and punishments that come through that exploration. So you could think of like kind of the classic science experiment of a rat in a maze. So as the rat makes its way through the maze, it might find cheese, which is like a reward, so it's like heading the right way, or it might get shocked, which is bad and a punishment. So then as the rat like does the maze again and again, it's trying to get more and more cheese. So that's kind of reinforcement learning. So now that we've hit an overview of all those, let's kind of do a deeper dive into each with an example. And for that, I want to deal with songs, I guess. So what I'm working on when I approach a machine learning problem, the individual like units, so the photos in my first example, the rocks in my second example, we like to call those instances. Each of those is an instance or an example. And then somehow we have to represent that instance or represent that example. And a lot of times we do that with something called a vector. Now, if you're not a big math person, a vector is just like a fancy name for kind of a list where each position in the list stands for something specific. So for example, if you have a song, you can have a vector that's the tempo of the song, whether or not it's rock, whether or not it's rap, the year it was released, whether or not there's an ocarina in the song, the duration of the song in seconds. And you can even have like categorical variables in there. So like, are the vocals a male, a female, or a duet, both. And then each of these things, each of these entries in the vector is a feature of each attribute. Is a feature of each feature or attribute of each instance, excuse me. So just for example, we could take a song like The Piano Man by Billy Joel, and we could have somebody encode this into a vector for us. So it's about 179 beats per minute. It's about 336 seconds long. I didn't verify this one, but I don't think it contains an ocarina. So we have all that encoded right there. And then you'll see also it's sung by a man. But we went ahead and encoded this as a 1, just because computers and a lot of these algorithms deal better with numbers than letters. So let's play with this in the context of supervised learning. I have a list of songs here, and some user, these belong to somebody's playlist, has given them a thumbs up or a thumbs down. So I have an idea of kind of what they like. So now I have these 2 songs at the bottom, and my job as a supervised learning algorithm is to decide, well, if I play these, is the user going to like them or not like them? So how do we do this? So we're going to take these and we're going to plot them. For the instance of this example, I just picked 2 features, so we could show this in 2 dimensions. So you have duration and then the beats per minute. If you want to add a third, you can imagine a third one coming out of the screen, but I couldn't figure out a way to fit that onto the PowerPoint super nicely. And then we could also extend the same thing to like 4, 5, 6 dimensions, but it's too late at night to think about stuff like that. So now, how do I decide where these question marks go? And how a lot of these supervised learning methods work is look at the data and they decide, all right, I'm going to draw a line somewhere to separate what I know. So I have a line. And how this line is drawn is what differs between a lot of the algorithms. So I kind of have my thumbs down side of the line and my thumbs up side of the line. So right here, it's looking like, okay, these two songs I know nothing about, probably going to be a thumbs up. But now, you can imagine a situation where we get a little bit more data. So we add that thumbs down right there. And now we can step back, and since we know a little bit more, it's looking like that top song might not be so favorable to the user. And you can imagine as we get more and more data in here, we're going to be able to draw that line closer and closer to the specific place. And again, this general concept extends if you're doing it in 3 dimensions instead of a line, you're drawing a plane. And if you want to go up and up, you can draw hyperplanes and all sorts of interesting shapes like that. So that's kind of a short intro to supervised learning. So next, unsupervised learning. I've got a playlist here. And you'll notice that there's something missing from the last time. And that's the thumbs up and the thumbs down. And that's kind of the difference here. Remember, unsupervised learning, we're learning from observation. So we don't have the luxury of having an expert, having somebody label the stuff as good or bad. So again, I can plot these songs. And now they're all question marks because I don't know which is which. And now let's say I'm trying to figure out, I know that all the songs in that playlist came from 2 genres. So now, which ones belong to which genre? Well, I don't really know too much about the genres because I wasn't given that information. But I can see kind of a trend here. And what you could do is, a lot of these unsupervised learning algorithms look for trends. So you could do something called like clustering these points, saying, okay, well, these 3 are pretty close to each other, and the other 4 are pretty close to each other. So we'll just go ahead and guess that like they share some underlying class. And then when we go back to label these, you can see the ones on the right, the ones on your left are all rap songs. And I think the ones on the right here were pulled from country music. But there's no way to say that's country or rap for the algorithm because it's not given that information. Again, it's just looking for, trying to mine those similarities in the data. So that's unsupervised learning, or learning from observation. So now we have reinforcement learning, which is learning from exploration. And this one doesn't fit quite as nicely into other things because, as you can see, we're not putting things into buckets, putting things into categories. We're like a rat running around a maze, if you remember something like that. So maybe bear through me with this example, and we'll try to get to a point, but it's not quite as concrete. So sticking with songs, let's say I'm a DJ. I was required to have one panda GIF in this presentation for the sponsors. So check that box. So I'm a DJ playing music, and I got to come up with a playlist for the party, right? I'm adding tracks to my queue, and I'm looking to optimize some reward, something that I get. So let's say that reward is the excitement level of people dancing. So I can come up with a function for that, and now that exact function comes back to that problem earlier of representation of like maybe number of people on the floor, number of people smiling, and like somehow measure like the amount of energy that's going on between them. So I find a way to quantify that numerically. So that's like my reward. And now the actions I can choose, instead of the rat in the maze picking the turns, are the songs that I get to play in the queue. So what order of songs is going to maximize this excitement score? And there's a couple interesting problems. There's a lot of interesting problems actually in this, but just a couple that I want to highlight. The first one being kind of the problem of how do I know what caused the excitement, right? So let's say let's say I play the electric slide, which always brings like 2/3 of the people there out to the dance floor. So I'm playing the electric slide, and everybody's out there. And then I play another song straight after that. Well, chances are a lot of people are going to hang around on the floor for one more song. So that's going to generate a decent amount of excitement. But now let's say like later on in the night, I play that song again. And because I didn't bring people out with the electric slide beforehand, there's a lot less excitement. And just given the excitement as you're going, it's going to be really hard to decide, or I guess one of the problems that's hard to solve is, how do I decide what generated that excitement? Because it's based on a lot of things other than what I just did. There's a lot of historical context in there too. Another interesting problem we have, it's called like the trade-off between exploration and exploitation. So let's say I'm like DJing the party and I'm playing a lot of like pop music and the people love it. Well, okay, so I'm playing pop. So when I come up to the next song, I have a decision to make. I can play more pop, and let's say that keeps the excitement here, right? Or I could switch over to something different, like something with more of a house beat. And that could bring the excitement up, but I also risk lowering it. So in this, basically, as I'm exploring, how do I decide to go with what I know versus trying something new where I could do even better, or I also risk doing worse? So that's kind of a big trade-off in the field. So yeah, you have supervised learning, unsupervised learning, reinforcement learning are kind of your three major fields of machine learning. And that kind of brings me to the end of the present section. And we'll just take a quick dive into the future, which shouldn't be too long because apparently it's impossible to see. So artificial general intelligence, or strong AI, as I might call it, because that's like less of a mouthful, is this fact that when can a computer get as good at the task that it's doing as a human? Some people like qualify or say this will happen, like when this happens, computers will become conscious. That's kind of a topic that's up for debate, and frankly, we could debate. But a lot of times there's these tests for this. The most well-known one is probably the Turing test, which is if I'm having a conversation with two people, or let's say I'm having a conversation with two black boxes. So I ask them a question, they respond, they say something back. Now the catch is one of those boxes is a human and the other one is a computer. And at the point where I can't tell those two apart, that algorithm, that computer, has attained what we're going to call artificial general intelligence, AGI, kind of the level of our thinking with that. One step beyond that actually is superintelligence, which is when the computers exceed our intellectual capability. Another one is the coffee test. So if I put like an agent, I use an agent as the term for something with artificial intelligence, down in a house and tell it to make me coffee, can it figure it out? And then one interesting one that I learned about when writing this talk was the IKEA test, which is given a package of flat pack furniture, can the computer build it? And actually, like from my experience with the IKEA at least, I'm thinking that might be able to be upgraded to a test for superintelligence, but not complete. That might just be me. And then finally, just a couple of the current limitations in the field. One is transfer of knowledge. So I have an algorithm that's really good at, let's say, playing chess, and another one that's really good at playing Go. How can I get those two to like teach each other? How can I make the chess algorithm good at Go and the Go algorithm good at chess? It turns out that's a lot harder problem than it seems. Another thing is security. There's not a whole lot of development and research into this area and kind of exploiting some of the things, some of the assumptions that these systems rest on and what they do. And then the final thing is so many examples are required to learn. I'm gonna come back to hot dogs. If I showed you probably like 5 or 6 pictures of a hot dog, and then gave you some more, you could probably pretty well tell me what a hot dog was, assuming you had never seen one before. But for a computer to do that, like if I'm giving that to some sort of neural network, it's gonna take thousands, millions of examples to get a level of performance that's even close to qubits. So it's a big question as to, how can we cut this? How can we cut the amount of data needed to train these algorithms down? So wrapping up, just to review where we came from, kind of talked a little bit about the definition of AI and through that, the definition of intelligence. We visited the past a little bit, talked about John McCarthy, and looked at the AI effect, came to the present, looked at some of those subfields, focused heavily on machine learning. We were talking about supervised learning, which is learning from an expert, unsupervised learning, which is learning from observation, and then reinforcement learning, which is learning from exploration. And then we looked ahead a little bit into the future, into strong artificial intelligence, into IKEA furniture, and then also into some of the limitations that we'll hopefully overcome someday. So as far as content goes, I think I kept it to my half hour so we could all get out and watch the Indians tonight. But I've got 5 minutes for questions if anybody's got anything.
What would you say are some like online resources that maybe have some sort of framework that maybe play with pertaining to this?
So the question was, what are some of the online resources that have some sort of framework that you can manipulate or play with this? So as far as like, do you mean like actually play with the algorithms themselves, or just kind of learn this sort of material?
No, I just want all the above. I mean, or whatever you feel like you could respond best to.
Okay, yeah. So for me, I'm going to take like online resources real quick. So Coursera has a couple good courses. There's a machine learning course out of Stanford that I think is really good on Coursera.org. Another site that has a few courses on it as well. These are like your MOOCs, your massively open online courses. Is Udacity, has like kind of an AI and then also a machine learning track. And I think those are available for free. And then
there's an introduction to AI.
yeah, there's one on edx.org as well, which is another one of those MOOC sites. As far as like playing around with things, there's a lot of like open source libraries freely available like around the web, and those have varying degrees of documentation with them. So if you want to chat afterward about kind of what you're interested in, maybe I can like give you some more specific examples.
To add to that, iTunes, you have Stanford's content open access. So if you go to iTunes, you can access all of Stanford's AI course content.
All right.
Yeah, the one by Andrew On is particularly good.
Yeah.
You haven't seen that.
Yep. Yeah, that's the one I was referring to.
One more question. So one of the things I've kind of noticed is it seems like there's a lot of kind of frameworks built around Python. Would you say that that's kind of the language leading the charge, or what would you say you've noticed in your research?
Yeah, for me, a lot of the research that I've done has been strongly built around Python. There's certainly other like frameworks and libraries out there. You're putting me on the spot, so I'm blanking on like non-Python things. But yeah, I would say I see a lot of Python.
Bill's right. There's a huge ecosystem around Python for all the data science and stuff. That said, the language R also has a huge number of libraries for all kinds of models and Bayesian stuff. And so it's worth looking at maybe a couple and see which one you like.
Yeah, there's a very large Python repository called like scikit-learn or sklearn, which contains like a ton of implementations of different algorithms. And that would be a great starting place if you're interested in just general kind of AI machine learning algorithms.
I have a resource that I'd just love to share and a follow-up question for you as well. It's a podcast I've been listening to in the car called Machine Learning Guide, and it's great. And it actually references the Coursera course and several other wonderful resources that I found in my like half of a month.
Awesome.
My question is, you mentioned the 4 parts in present AI and machine learning. Could you give an example of the knowledge representation and reasoning and how that's used? What's the application of that?
Yeah, sure. And those by no means like a complete list. Those are just like 4 kind of subfields that I sampled. But when we come into like things like knowledge representation, like at least to me, that's this whole problem of, okay, I have a song. I could do it as like I could somehow pass the waveforms and stuff like that into a computer. But I could also do this thing where I come up with the different features for it, and then which features do I want to have on the song. So like I could include something like the eye color of the artist, but that's not going to lead to a very good performing algorithm if I'm trying to classify songs. So that's kind of taking, taking these things and how do we encode that into something to give to our algorithm to think about. Does that help clear things up?
I'm gonna have to dig a little deeper.
Okay. Yeah, sounds good. We could chat about it a little bit afterward.
I appreciate it. Thanks.
Mm-hmm. All right, time for one more, if there is one more. All right. Well, thanks for listening, and let's hand it back to Jason.
Thank you, Billy. That was excellent. Okay. Also, to kind of follow up on the educational resources section, as part of my talk, I have an appendix that I'm not going to go over tonight. These slides up, and at the end of the appendix, there will be a complete list of all the resources that I've found personally helpful, and I think it's not a complete list, but it's as close as one can put on one slide. So, okay, so my name is Jason Mancuso, again, and deep learning. I studied math at John Carroll, and while I was there, I had an amazing opportunity to learning with Dr. Elena Manelich and with the Cleveland Clinic. And that's kind of when I developed my interest in machine learning and deep learning in particular. A little bit about that project will kind of help illustrate that. The clinic processes millions of blood samples per year in its labs, and thousands of these samples are contaminated, which can skew test results and lead to incorrect medical treatment. So because of the quantity of samples, millions per year, no one can go through these samples manually. No medical expert, like a doctor, can do this physically by hand. So we needed something automatic that could catch these efficiently. And we wanted to create a machine learning algorithm to do so because we thought we had a pretty good shot at doing that. We tried traditional machine learning techniques, classical machine learning, and they performed well, but not well enough to catch all the samples that we wanted it to. So that's when I trained my first neural network, and it was a success. We accurately identified a ton of contaminated samples, and we virtually solved the problem at the clinic.
What were the difference in rates from before and after? Like before you used machine
before machine learning or
deep learning? Deep learning.
Okay. I think it was a relative increase of about 10 to 20% in contaminated samples. The clean samples, I guess, were easier to classify for all the algorithms, but doing that correctly while catching the contaminated samples was the tough part. Yeah, it's a very small percentage of all of the samples out there, so they're harder to catch. And we can talk more about that. Sure. Yeah. So that was my first exposure to all this, and I loved it. And since then, I joined Pandata, and I build really cool models for them. And yeah, and I'm also a mentor of the Udacity Artificial Intelligence Nano degree, where I'm able to teach students across the world about AI. So that's how I got interested in all this, and that's why I started this meetup. So AI, there's a lot of hype right now around it. It's blown up since 2012, in particular. And this is really well measured by attendance at the Neural Information Processing Systems Conference. This is the premier deep learning conference throughout the world. And attendance has more than doubled over the past 2 years. Specifically this year, that graph on the right shows the registration over each year and the timeline until it's sold out. Most of the time it sells out within a week or two of the conference. This year it sold out before early registration ended, a month before early registration ended. That's never happened before. And that's what happened this year. And this emphasizes the growth that we've seen in AI recently, and in particular, due to advances in deep learning. So what is deep learning? It is a set of methods to using deep neural networks to perform machine learning, which means it's a subset of machine learning, which we just talked about. The key difference between classical machine learning and deep learning is in representation, which we covered quite a bit with Billy. At a high level, though, representation is how a model detects patterns from the data it's given. It's what the model works with directly, and it's what it uses to learn its predictive ability. And here's a picture of the classical machine learning workflow. The most important part for this is that feature engineering step. This has to do with the representation, which is limited by human imagination in classical machine learning. And it's handcrafted through that feature engineering process. So for an example, suppose we wanted to predict the price of a house, and we had a list of houses, and we had the square footage for each house, and we also had the number of bedrooms in each house. One thing we might do is engineer a feature, the average square feet per bedroom, by dividing the square foot for each house divided by the number of bedrooms. And that would give us this extra feature that we didn't have in the representation before we did that. And doing that might improve the performance of our model because it now has more information to work with. And this works. When you do this a lot for a lot of different features, it does work, but it's a time-consuming process. And it also is a suboptimal way of going about predictive modeling. And that's what deep learning attempts to avoid. So it automates this feature engineering step, and it learns the representation with the model. What we lose in interpretability by creating those features by hand and knowing what each one means, we gain in performance. And it typically works as well or better than competing models in these problems. This is kind of the paper that, one of the papers that started deep learning, or at least made it influential. Geoffrey Hinton from the University of Montreal, he's one of the founding fathers of deep learning, and he details this type of representation learning with neural networks in this paper. It's a little bit beyond the scope of this talk, but I wanted to flash it up on the screen, and we'll kind of go over what he talks about at a high level now. So suppose we're in that supervised learning context that Billy talked about. We have data, and it's labeled. For example, we have a set of labeled blood samples, and we know whether each one is contaminated or not. And our goal is to predict whether each new blood sample we haven't seen yet is contaminated. And we're going to build a model to do this. And with the neural network, this is how it works. So these are two neural networks. Let's kind of focus on one of them. And what we do is we start by feeding the data into that red layer, that input layer. The data flows through the blue layers until it reaches the green layer. And at the green layer, a prediction is made, so contaminated or not. And then we measure, at that point, how good the prediction is with respect to the label that we have. And then we adjust the rest of the network based on how well we did. And repeating this process over and over allows the many blue hidden layers there to learn a useful representation for prediction. So it essentially learns through repeated trial and error how to predict whether a blood sample is contaminated or not. And this is a demo of how this works. Ooh, I gotta get this. Give me 1 second to get this up. Okay. So this is ConvNet.js. It's a neural networks library written in JavaScript by Andrej Karpathy from Stanford University. He's now actually the director of AI at Tesla. But you know, this is a toy data set. These green dots represent, let's say, normal blood tests, and the red ones represent contaminated blood tests. And that line right here is the decision boundary, or the line that we're using to figure out whether or not a sample is contaminated or not. And what is happening is it goes through the network, it sees this data, and it gets pushed through the network. And these are each at different layers of the network. And what you can see is it's being transformed as it goes through the network in different ways. And at the end, it looks like this. And how this works is now we can draw a straight line through this. It has learned a useful representation where it can distinctly classify the points in one way or another. All these red points, these are classified as contaminated and the rest are classified as normal. And so that's kind of how, and it learns that representation. It learns to do that on its own. So it's going to be hard. So that's how a neural network learns. And if you want to check that out, we'll have a link to that in the slides. So you can play around with different kinds of data and see that kind of thing. So this works. I've been continually claiming that it works on a lot of problems without really giving you any evidence. But there have been some pretty amazing breakthroughs with deep learning, and we'll go over a few of those now. So in automatic speech recognition, significant improvement hadn't been made in 10 years. As you can see, that plateau there between 2003 and 2013. And in 2013, the first neural network was trained for this task for recognizing speech, converting from vocal speech to text. And clearly it dropped significantly, and now Siri, Alexa, Google Assistant, they all use neural networks in their speech recognition software. The same is true for translating languages and natural language processing. Again, a similar situation where progress was very slow for the past few years, and then in 2016, a new neural network was applied to this task, and it significantly improved BLUE scores, which is a way of evaluating how well a translation is, or how good a translation is. And now Google Translate runs on deep learning, and recently they announced that Google Pixel Bud will be able to do this in real time based on Google's networks. And then image recognition, this is kind of the canonical example of where deep learning has really helped. There was a breakthrough in 2012 where it cut the error rate of kind of a standard benchmark for image recognition in half. And now we're at the point where these networks do better than humans in recognizing images for certain tasks. And that's, again, due to deep learning. And finally, this is my personal favorite. It's really inspirational to me. This was AlphaGo, which was an AI developed by Google's DeepMind using deep learning. It defeated the world's best Go player, Lee Sedol, 4 out of 5 times in 2015, I think. And it's gotten better since then. It no longer loses at all to anyone. And experts thought this wouldn't happen for 15 years, and we did it 2 years ago with deep learning. So why does deep learning work? It's a hard question, and no one really knows the answer. But there's a few ideas. Recall that in supervised learning, we're trying to predict labels from data that we haven't seen. And we do so by building a model, and that model can be considered a function that predicts labels. And there's a mathematical justification up on the screen. Basically, it just says that any continuous function can be approximated by a neural network. And that's true. We don't always have the data or the algorithms to do it, but it is theoretically possible. And we've found that basically deep learning systems, they can detect complex patterns that humans can't easily detect by learning the representation. So this is an example of a representation learned by a neural network. It's a facial recognition network. And so the network is looking at raw pixel values at the beginning there on the left. And its first kind of transformation builds those edges and those curved lines. Those are lower level features that are learned directly from the pixels. And then the next layer combines those features into kind of more complex, but still not fully complex features, like it might be the part of an eye, the part of an ear, part of a nose, etc. And those still aren't enough to completely classify a face, but then when you compose those together in the last layer, you actually get faces. And this is the representation that the network has learned and is is using to classify these faces. And that's all learned. We didn't have to tell it to do that. It did it by itself. So, I mean, this is kind of misleading in some sense because these hidden layers are not always interpretable like this, even in image recognition. Sometimes you don't get these nice features that you see. But the compositional process for how you compose lower level features into these more complex ones is always the same in every neural network, and that's how they work. So again, this process of learning features, learning the representation, is quite different from classical techniques where we're handcrafting the features, like the housing example. And that's the reason this works, I think, is because these features that we handcraft have to be human interpretable because we crafted them. For a machine, that's not the case. It can learn a representation that is not human interpretable that may be useful to it. Computers use different representations than humans do, and we're not really that good at guessing what a computer needs to do its job. Why not let the computer do it? So that's the core of my talk. Some disadvantages of deep learning are up on the screen. They're hard to train. It's kind of a black art. It takes a lot of work to get them working. The model architectures and training, it all depends on the data set. And there are a lot of current research directions on solving this and making it easier. For example, automating the procedure and automating network creation and tuning everything. And you can read about that. They take a long time to train. They're very computationally intensive. So we've developed actually GPUs, and Google has its own tensor processing unit that it's developed in-house that does this too. It speeds up training or inference of these models from 10 to 100 times, so it actually makes it feasible to work with. And also open source libraries that we can use make the coding of these algorithms a lot simpler, and they interface with GPUs and cloud instances so that we can speed up our own training of neural networks. And also, the last disadvantage is that you're trading interpretability for performance. So sometimes you want to build a network or a model that you can interpret, that you can get insight from. And sometimes you don't need this performance boost. But when you do, that's when this is useful. So I know there's a lot in a short amount of time, and I'd love to answer your questions if you have any. Sure. Yes, it has. There's a couple things in that research direction. Actually, Google just recently announced that they call it AutoML, automatic machine learning, and they announced that they were able to beat all experts on this particular task with their AutoML framework. So that is definitely in the horizon. So we might be automating ourselves out of a job, but it'll be good for all of us, I hope. So, excuse me. It's very recent. It's like within the past few months they announced that. I don't even think they published a paper about it. So, and there's been work in the past too using reinforcement learning to do this. There's a technique called NEAT, Neural Evolutionary Architecture Training, which tries to design the network for you as you're training it, and that's been around probably for 10, 15 years. So there's been a lot of work in that. Yeah. Sure. Sure. So the question was, how do you know that these algorithms are successful when you're applying them in practice? So what we do, we have a training or a data set, right? And before we do any modeling, we split the data set into a training set and a test set. And we use the training set to train the model. That's what the model learns from. But then after we're done, and sometimes you do an extra set so that you can try a bunch of different models. But the idea is that you train on that stuff, and you have this other set that you haven't even seen. It's almost like new data that could be coming in through a production system were you to implement this in the real world. Yeah, it's kind of a set that's unbiased that will give you an accurate measure of how this would work in the real world. And there are also some like concerns about is the data set that you have a true, a good representation of data that you would see in the real world. But that's the kind of the best we have as far as evaluating them, and it works really well in practice. Yeah, so the question was about when we say this, it's learning by itself. We actually initiate that learning procedure, and yeah, we do. There's a lot of different algorithms that you can use, but you do have to write the code. But once you write the code and execute it, it learns the patterns from the data, and then you can use that model in other code to accomplish tasks. So.
No, that's you get pre-trained models from like we do in some of these shops, right? And you can actually retrain parts of it that you can include or exclude to the layers of it, you know.
Mm-hmm.
You can add it to retrain certain layers specifically for your problems.
Yeah. So what was mentioned was that transfer learning is huge here. That's called transfer learning, and it's basically when there are these massive data sets that would take weeks to train a model on, that these big companies do constantly. Every year they're training on these data sets to get better and better models. And what we can do is download those models that they host online for free and use them for our own projects. And we do that. And this is also helpful when you have a project where maybe you can't access the data that you need, or you're limited in the amount of data you have, and you don't have enough data to train one of these networks on your own. You can assemble a data set, an external data set, train on that, kind of get your representation learned, and then transfer it over to the small data set. And you don't necessarily need to get this from a big company, is what I'm saying. You can do this on your own if you have access to that data. So yeah, that's a huge part. And I think it was in the slides. I just kind of skipped over it. Yeah. Mm-hmm.
How do you know? Maybe I am not. I'm going to take what and then say, all right, now, tell me which one do you think is something really good?
Right.
So
So there's so the question was, how similar do the data sets have to be that you transfer from and to? There's a couple different answers to this. One, so when you're doing standard transfer learning, just from one data set to another, they typically have to be the same format, same shape. So if you're doing images, like maybe you can train a network on ImageNet, which has 1,000 different categories, and then you're going to transfer that to tell you if a picture is of a cat or a dog. And you can do that fairly easily. And those are pretty similar because there are cats and dogs in that original data set. But even if there were no cats and dogs in that data set, you'd still be able to do it. You would just you would cut the network off, the pre-trained network. You'd cut it off a little bit earlier because that has less features that are specific to your data set. So for example, the faces. Earlier on, there were just edges and lines, and then there were noses and mouths. But maybe between the noses and mouths and the edges and lines, there's a more useful layer there that can be used for your cats and dogs. So there are techniques to doing that. The second answer to that is that current research is a very active area of research, transferring from like something that can do images to something that can do songs. There has been some research. It's very slow and it's very new. But DMind released a paper about this. I can't remember the name of it, but I can post the link on our channel and you can take a look at that. But it is possible. It's been done in a limited setting. But yeah. Yeah. Can you speak up a little bit? So are you asking if it can realize whether it needs more data? Sure. Not yet. I think that's a behavior that is pretty far ahead of what we can do currently. There are ways you can diagnose whether a system needs more data, and if you are careful about it, you can figure out what it might need and go look for that yourself. Because learning patterns to predict, so these networks are very specific to the task they're trained on. And even with transfer learning, you still have to be close to the original task. And like I said, we're very far away from ever having something that can transfer that far. From like, oh, I'm looking at cats and dogs, to, I want to learn about fish, but I don't have any pictures of fish. Let me go find fish. That's a very complex sequence of behaviors that humans can do pretty easily, but that we don't have a way of doing with current technology. I wish I had a better answer for you, but that's kind of what I know. Sure.
So you kind of trained a computer program to get all that data, you guys have to go out
So there are a ton of data sets online for free of varying quality. A lot of companies do make a living off of collecting data from the internet and going through the whole process of labeling it, cleaning it, and preparing those data sets. But there are also a lot of open source initiatives around doing that too. For example, there's a website called openml.org, and they host thousands of data sets that are pretty much already prepared and ready for machine learning. I think they even have like an API that you can use through your favorite language that will load the data set, and you can select from, you can manually create your experiment within their framework and test it on 100 data sets at a time. So and that's just one example. There's the UCI machine learning repository, which is kind of like a classic place where you can get all kinds of data sets from like the 60s to today. And I can post links to those resources. And also Kaggle is a huge one. Kaggle is a really great learning resource. It's a huge community of data scientists and people trying to solve machine learning problems. And they host competitions. Like they're always coming out with a new competition, pretty much every couple of weeks. So I'll post links to all that. Okay, is there any other questions? Any other questions? No? Okay.
Take a 5-minute break.
Sure, we can. Yeah. Yeah, let's take a 5-minute break. We'll come back and we'll see Kevin speak. Thanks.
Okay, well done. Good suggestion. Thanks. Take what the defense is doing. Actually, we don't have to. What do you think this year? No, I'm done. I'm kind of. Yeah. Awesome. Yeah.
All right. I think we're ready to start back up. If everyone will take their seats, and we'll get started very shortly.
Alrighty.
Yeah, so I guess just give it a few minutes.
Yeah, that's all right. Yeah. I figured people want to get up, stretch their legs.
That was a good call. Yeah, thanks.
Okay, I guess, it's on. Hello, can you hear me okay? Time to get back into it. So this is me, Kevin Cartier. I'm currently doing some contract work at IBM Watson Health, just down there at Superior and 12th Street. And prior to that, not too long ago, I was out at CAIG doing some project management in their Department of Genetic Epidemiology. Spent a few years studying with Shomo Wright in the machine learning department and Andy Podgorski. Are they still out there? Yeah. All right, cool. I want to talk later. Yeah. So, so I got a background in machine learning, statistics, computer science, mathematics. I've been around the sun many times, and so trying to make sense of it all here. So I didn't bother putting together a slide. You can go find me on LinkedIn if you're really interested. All right. But out of curiosity, I'm just wondering who's in the audience here tonight. How many people with like statistics or mathematics degrees? Just quick show of hands. You, okay. IT, computing, networking kind of stuff, yeah. And like business, business analysis, marketing, that kind of stuff. Okay, so it's kind of a nice mix. All right, good, good. All right. So I want to say thanks to Jason and Pandata for inviting me here to speak tonight. This is really cool. The whole thing, the AI group, is a great idea for lots of reasons, not the least of which is when the singularity finally happens and the robots take over, all right, everybody in this room is going to be on the right side of the microchip. You're good, okay? So you got nothing to worry about there. That said, all right, as Jason kind of alluded, are we really putting ourselves out of a job with this? When's that going to happen? And, you know, I think we still got some trench warfare going on, trying to figure out a lot of this stuff. So this is some of my own experiences from the trenches, things that I've had to deal with, the kinds of problems and issues that I see, you know, and I have seen a lot in trying to do data science or machine learning or computing, right? And so what I'd like to do is take you through some of the things that I've dealt with in a talk called Machine Learning in the Trenches. So first of all, right, so you problems to deal with. The stuff that I want to talk about is not so much the algorithm, right? You know, you can read the book from Tib Sharani and write the algorithm in Python or R and get that sorted out pretty quickly, but you find out, well, if in a real world problem with real world data, right, you're going to have some quality issues. Good luck there, buddy, okay? And then just by the sheer size of the kinds of data we're trying to deal with anymore, you're going to have a problem maybe sorting out the signal to noise, right? Or on the other side of it, you know, if you're looking at lots of dimensions, like in NLP applications or medical applications, financials, right, whatever. So you can end up with, you know, spurious correlations or dimensionality issues, which we'll get to, right? Model selection. Everybody, who are my statisticians? Type 1, type 2 error. You ever learn about type 3 error? Okay, that's a thing. I'm going to tell you about it, right? Model interpretations. We're going to hear from our old friend Donald Rumsfeld once more time, okay? And something called the black swan. Anybody ever heard of the black swan theory? Cool. Oh, you guys are right there with me. I like this, okay? And finally, a method for the madness, okay? Like, is there any hope at all? I don't want to depress you too much with all this stuff. Nope, that's boring. Okay. So, but first, the 800-pound gorilla in the room, right? Big data. So, and you know, you can read the definitions, the 4 V's, and again, we're not going to get into all that. But the fact is, increasingly, that's what we're being asked to deal with, okay? So let's take a look. You know what, the reason I can't see, so I don't have my glasses on. Here we go. Okay. So yeah, back in the day when it was just data, think about, you know, how things used to be, right? The data was pretty much controlled by the enterprise, right? Data typically were characterized by homogeneity of record types, predictable rate of acquisition. You kind of knew, you know, how fast it was coming in, right? I'm talking maybe 30, 40 years ago, right? And relatively manageable quantities and scales. This is the point, right? You had a situation where the customers pretty well conformed to the structures laid down by the business. Just like these birds, they find the wire, they sit on the wire, okay? So think about that picture for just a minute. And now let's take a look at what it looks like today. There's your wire, there are the birds, okay? And this, I think, is a pretty accurate depiction of what's going on with your data, your market, your customers, all that, right? So what's going on? Well, the customers are coming at you, whether you're ready or not. Multiple channels, international, 24/7, right? Here they come. And they don't care about your structures, right? They got Twitter, they got web apps, they got all kinds of stuff. So their preferences pivot quickly. You know, their opinions, it's very dynamic, very rapidly moving, and you got to work pretty hard to keep up with this, right? But here's the interesting thing, all right, and why I kind of like this little bird picture so much. Yeah, they're not sitting on the wires, but there's still a pattern here, is there not? But the pattern is dynamic, it's changing, but you could say, well, there are clumps of birds, and maybe I need to think about that in terms of market preferences or what the customers are doing and so forth, okay? All right, so this is one of my favorite pictures, and maybe I can wander over here. So think about, I made this up, okay? Full disclosure, there's no such thing as the fundamental theorem of big data quality, except this room at least, okay? And what I claim is, without proof, right, the vast majority of the given data collection may be irrelevant, misaligned, or otherwise incompatible with respect to the existing systems, platforms, and the problem at hand, okay? But why do we say that? Well, this is kind of what's going on. So here's your big data collection reported in from websites and, you know, Facebook feeds and news, whatever, right? You got all kinds of log files, all kinds of junk, right? You're gonna pull it in and get some gold nuggets out of there. Data's the new oil. You know what they're saying? So what do we got? Well, first of all, here's everything. A lot of it is just like shot with missing this. You can't even read this stuff. It's just total trash. Like, throw that away. And then the rest of it is interpretable, but it's irrelevant for what you're trying to do, okay? And then some of the stuff is relevant, but then there's some of it is informative. It's non-redundant. So let's take this yellow ball and blow it up, okay? Now, so what's left? We've got It's the uninterpretable stuff, forget that. And then here's the stuff that we can make sense of, okay. But again, a lot of it is still irrelevant to what you're trying to figure out. And so what does that leave you? Well, here's your signal, all right? And somewhere, after you separate the signal from the noise, there's this little nugget, right? And that's the stuff that gives you the insight that you're trying to figure out, okay? So that's the problem, all right? Well, here's another problem. The holy grail of data quality, this is what you want. Oh, this is beautiful. It's nice 2x2 table. And by the way, I don't care if you're using SQL or SAS or R or Python, I don't care what you're using. At the end of the day, more often than not, you need to get your data looking something like this. Usually, about 99% of the time, you're trying to get your data into some kind of 2x2 table, with each instance is a row, and then the different features or attributes are on the columns, right? So if you've ever played around with an Excel spreadsheet, well, if you find yourself doing data science or anything else, you're still trying to get something like this, okay? That's just the way it is, right, for now. And so what? We're trying to get data quality, accurate and timely and complete and aligned and have all these data quality metrics. Big data stuff, there's all these same requirements, but everything's magnified. The challenges are just magnified, okay? So, where does that leave us? Well, one other thing to keep in mind is, okay, we want this data quality. What do you have to do to get there? Well, this is some, by the way, I did a lousy job of giving attribution of these pictures, so I might have to clean this up before we put it out on YouTube, at least give proper attribution or something. In any case, this is from Ford's Fortune article, I forget. What do data scientists spend most of their time doing? Cleaning the friggin' data, okay? Anybody want to tell me otherwise? Okay, thank you. And what is the least enjoyable part of data science? Cleaning the data. Oh my God, I gotta write another script to parse out all the junk that's not supposed to be there in the first place. Yeah, so that's it. And then predictably, the part that everybody likes, mining for patterns and building the models, that's like 3, 4, 5%. So you're doing all this other stuff, building the data sets. And, well, make no mistake, this is not just important, it's critical. You're going to get nowhere unless you do all this other stuff. Or yes, and this is the real problem, you can maybe kind of shortcut this or throw it off or whatever. At the end of the day, you're going to have a result, and you're going to go to the boss with the result and say, look what we figured out. And he's going to say, what? Bull, right? I'll believe it. Show me. How do you know, right? So unless you've done the due diligence on this, you're going to have a hard time convincing somebody to invest $50 million in some portfolio or whatever it is you're trying to do, okay? So pay attention to the quality, okay? All right, so stepping away from quality then, talk about signal versus noise issue for just a second, because again, when you have that much data, we saw that the circle, there's this tiny little bubble or dot inside that's like, okay, that's where the signal is, but there's all this noise you have to cut through, okay? So for me, it's like, I don't know, I remember the first time I went to a TGI Fridays restaurant, and I remember thinking, this would be a good place to go with somebody I don't want to talk to, okay? Because it was so noisy in there, Maybe it's different now. I haven't been there in a while. In any case, so think about what's going on. The waiter's trying to tell you, well, this is the special of the day, you have tomato soup or whatever, and you're trying to figure this out over, with all the background noise. So think about what humans do. We kind of know what we think he's telling us, special of the day, whatever, and we sort of focus on what we expect to hear, and at the same time, trying to ignore everything else. So in mathematical terms, this is kind of a Bayesian approach, all right? You give a bias, so it's the bias variance trade-off. What we look at. you're sort of giving a bias to what you kind of expect to see, and it helps you do a better job of nailing it on the words. I'll show you a nice little example here. This is my favorite example, not just about how Bayesian mathematics or statistics work, but how machine learning works. I could even explain this to my mother. Okay? So what is this? In a text stream, think about spam. Is spam really a problem for anybody anymore? It's a solved problem. Why is that? Because we gave it over to the robots, and we helped them because Google and these other browsers, they put a button in your mail thing. And when you see spam, you go, bam, that's spam. Okay, get out of here, right? And that is how we are teaching collectively with millions, billions of emails, lots of data. That's how we're teaching the robots the difference between, you know, a nice letter from Uncle George who wants to offer me his old Rolex watch and a spam, okay? And then just quickly, the way this works, if you remember the Bayesian probability, you say, well, we want to know what is the probability that email is spam given that I see the word Rolex, the word offer. Well, it turns out that's really hard to calculate. Okay? However, thanks to our old friend Thomas Bayes, you can flip this whole thing around into something that is easy to calculate. And what we say is, well, forget that. Let's restate this as, what is the probability that I see the word Rolex in a spam message times the probability that I see the word offer in a spam times the general, you know, prevalence of spam, right? And you divide that by what's the probability of the word Rolex, the word offer, blah, blah, blah. You do the math, and then you get a number, okay? And this is, you know, by and large, how we do it. My own opinion, my guess is we're going to solve the fake news problem pretty much the same way. Never really good at it, okay? Okay, what about correlations? In this case, spurious correlation. Maybe you take your stats class, they teach you this mantra, correlation is not causation, right? You learn this, hopefully you learn it. It's easy to learn, easy to say, and easy to forget. In the heat of the battle, you're doing all kinds of analysis, you're trying to, you know, get your reports together, and you say, oh, I got an association, I got something, I got a lighting, I found one. Well, here's the problem. When you're looking at lots of dimensions, right, big data set, just by chance alone, there's a good probability that two variables are going to be correlated, okay? And so you have to keep this in mind and have a sense that, well, there are ways to figure this out. To understand, is that a real thing, or is it just correlation theories? What do we got here? This is a fun website to go to, by the way. You've never seen it. All kinds of fun little examples. This is the correlation of the divorce rate in Maine with per capita consumption of margarine. So, you know, if you're thinking, well, I'm saying people get divorced, then they eat lots of margarine, or maybe people eat too much margarine, hate each other, I don't know. So it's kind of silly, and there are lots of kind of fun examples of this based on, you know, actual sensor data and demographics data.
That's real data.
Yeah, well, yeah. You think I'm making this up? Yeah. What are we doing on time? We're all right. Okay. Yeah. Okay. I like this one a lot. So, can you trust your eyes? Trust the evidence of your eyes. Seeing, believing, right? It's in the scripture, right? So, it turns out that this is really, even studying psychology and stuff. Okay, so, the psychologists have a term called pre-attentive processing. You know that the hairs that rise on the back of your neck and you know you're being watched or whatever, or just the ability to see a pattern, especially hopefully the pattern of a lion hiding in the weeds, or just a face, you know, among many. So our cortical cortex and so forth is tuned by millions of years of evolution to be able to do this really, really well. Sometimes, right? because sometimes we see faces where really maybe there isn't a face. So this is a famous picture. Anybody know what this is taken from? Mars. Very good. You're on this. Okay. Yeah. So people saw this and said, "Wow, there's a human face on Mars. What does it mean? People out there or something? What are they trying to tell us?" And then, of course, the famous image of Jesus. I don't know, a grilled cheese sandwich. I've struggled with the theological implications of this for a long time. I just don't know where to go with it. But the bottom line is, okay, but here's something you may be more likely to see, some plot. Here's your scatter plot, here's your data, and you look at this and say, well, is there a pattern there? Yeah, maybe, kind of. I see kind of this clump of red. Maybe there's something there. Okay. So, okay, can we trust our eyes? Yeah, maybe, no, I don't know. Well, then we have to go ask the computer and say, well, show me the numbers. It's all about the numbers. Well, maybe. So have a look at this set of 4 data sets. Right? Here are 4 data sets. Data set 1, 2, 3, 4. X, Y. Each of these 4 data sets has some interesting properties. Each one has the same mean value for X. Mean value for X is 9 for this one, for this one, for this one, and this one. Okay? The sample variance of X in each one is the same. The mean value of Y is the same, and so on and so on. Okay? Now, ask yourself, okay, we're going to plot this out. You expect the plots to all kind of look the same, wouldn't you? I mean, with all these statistical similarities going on. And yet it turns out, no, they don't look the same at all, do they? Right? Now, this is admittedly a contrived example. It was developed by a statistician named Francis Ascom. It's called Ascom's quartet. Okay? But it's a really great example of how the numbers can fool you just as well as the pictures, right? So what we got here? Well, this is what? Just a kind of a nice linear set with an outlier. This is kind of a linear set, looking good. This is non-linear. This is also non-linear with an outlier. Or it's linear with an outlier, whatever. So but the point is, I guess you have to look at both, don't you? You got to look at the plots. You got to look at the numbers. And mostly you got to use what's up here. And your understanding of, well, not just math and stat. It's like, well, what's going on in the business? Subject matter expertise, right? You got to have people in the room that know, well, what is this all about anyway, right? If you get too buried in all the numbers and stuff, you can get lost in a lot of, wasted time, if nothing else. The curse of conventionality. So this is not the next Star Wars movie, okay? This is also a real thing. With real mathematics, don't worry about this formula, right? It's the matter. The point is, it is a real mathematical thing that has to do with the fact that, remember the picture of the Excel spreadsheet, right? Each row is a different example. For instance, each column is a different dimension, right? And the more dimensions you have, the more trouble you're likely to get into. So what the curse of dimensionality says is, as you have more and more dimensions, you basically run out of center. There's no middle. There's no average representative instance anymore. All right? There's no such thing. So this is kind of bad news for clustering methods, right? We saw some examples of that earlier. Yes, clustering methods are great, but you have to be aware that if you try to do clusters on 10,000 dimensions, well, maybe you're going to have a hard time finding the exemplar, right? And I can show you kind of a neat way to think about this. Yeah, well, this is kind of walk through this. There you go. So think about, everybody goes back to the stats course and the bell curve, and remember, this here's your 6 sigma spread, right? Okay. Now think about what we learned, that underneath this bell curve, right, all the different possible values, right? So 99%, 99.4% of your probability or of your occurrences, it's going to show up within this 6 sigma region right here. Boom. Okay? Great. So let's call that the middle. I don't even have to go right to this goal. Give me that whole big thing. That's the middle. Now, in one dimension, what's the probability, all right, that I get a value from the middle? Well, it's 99.7%. That's the probability of getting something from the middle. One dimension. Now, what if I have 2 dimensions? What's the probability that I get something from the middle on each dimension? Assuming orthogonality, okay. Well, that means you just multiply, right? The probability that the first one is in the middle and the next one is in the middle, well, that's 0.9974, 0.9974 equals 0.9946. And you carry this forward to 20 dimensions, and it becomes 0.9974 to the 20th power, which is 0.94. Well, that's quite good. Yeah, but wait, right? Because you already know where I'm going, don't you? What about 1,000 dimensions? 0.9974 to the 1,000 power is 0.07. So now suddenly you have pretty low hope of getting an average point. And you'll say, well, I'm not going to have 1,000 dimensions. Well, then you haven't been playing with big data very much, because this stuff happens all the time, right? All right. So where are we now? Oh, yes. Okay. The other thing you learn in basic statistics. Okay. Basic stats, the confusion table, right? I always loved that, right? Because I always felt confused when I was taking this stuff. All right. So it's like, okay, well, what is the predicted response? Is yes or no? The actual response, whatever. So it's like you have these true positives, false positives. So what the type 1 error means, well, a false positive. It's an alarm without a fire. It's a type 1 error. Okay? And a type 2 error is a false negative. That's a fire without an alarm. All right. But what about a type 3 error? What if the model is just wrong? Okay? You say, well, what the heck are you talking about? Well, look at this picture here. Right? So here's our model. This line is our model, some kind of linear pattern. And sure enough, well, yeah, it really classifies it. It classifies the red ones, right? So all the red ones are on one side of the line, and these blue ones are on the other side. So I guess it did an okay job, but clearly not, okay? Because the data are not linear. So here we are trying to apply some kind of linear classifier against non-linear data. So we need a circle or something to get on this, right? So you've got the wrong model, right? What does that mean? Well, it's like my father used to say, you ask the wrong question, you get the wrong answer, okay? So you want to be aware of type 3 error. And now to our old friend, Donald Rumsfeld. Anybody never heard of this quote, that the unknown unknowns? This just never gets old. Yeah, so he was talking, he was the defense secretary under a couple of presidents in 2002. He said, yeah, reports that say something hasn't happened yet are always interesting. The known knowns, we have the known unknowns, and the unknown unknowns. The stuff we don't know, we don't know. And if you look throughout history, it's the latter category that tend to be the difficult ones. This is important because, those of us who are trying to call ourselves data scientists, well, the science part of that implies that you're exploring into the unknowns. Sooner or later, you're going to stumble across something that nobody knew before. And hopefully that's a good thing, like a market opportunity or a way to run the operation more efficiently, or a way to make money that nobody thought of. I don't know, whatever it is, it's like, oh man, nobody ever even thought of that before, right? That's what you're hoping to get by doing all this data mining. So you do have to understand that that's hopefully part of what's going on. There is such a thing as black swan theory. So about 10 years after the Rumsfeld quote, this guy Nassim Taleb wrote a really neat book called The Black Swan, and basically he came to the conclusion that in the history of human experience, at least, we have these black swan events that are defined or characterized as follows. They are almost completely unexpected beforehand. They have a major impact on behavior, thinking, etc. And they are eventually, after the fact, perceived as, oh, you know, predictable. Oh, we should have seen that coming. So let me ask you, can anybody think of a black swan event that happened in this country, maybe back in November? I'm just saying, okay? So I'll let you ponder that. I will show you my particular favorite example of a black swan event. Anybody into astronomy? This is just so cool. In 1995, astronomers pointed the Hubble telescope at what they thought, it's a little speck of sky. Not like take a drinking straw, hold it at arm's length, try to look through it, and that's about the size of the sky they're looking at, okay? And they looked at what they expected was just an empty void of space. And they set the exposure on the camera for a week or whatever it was, and lo and behold, they ended up getting a picture of somewhere around 3,000 galaxies. Okay? This is known as the Hubble Deep Field Experiment. So the point is, you know, you go out doing science, you do it the right way, you end up learning stuff that, well, this totally revolutionized astronomy thereafter, okay? It changed everybody's thinking about where we are and what's out there and what else could be out there and how the universe is put together. And so just something to keep in mind. So we're kind of getting ready to wind this on down, okay? Because, you know, Kluber is going to be pitching if he's not already. But what I'd like to do then is step back from talking about all these different kinds of issues. Well, what do you do about this, right? What's a smart way to go about wrestling with, you know, big data, quality issues, and spurious correlations, and how do you protect yourself and your organization against the ill effects and waste of resources, crashing around with this, and how do you take some steps to guarantee you have a shot at getting something good out of the process. And I claim that you should have at least have a look at a methodology called the cross-industry standard process for data mining, right? And it's, on the surface, it's pretty simple, and you say, well, it's kind of obvious. Well, we'll talk about obvious in a second. But what it says is, first of all, your data mining process, or for which you're using AI, and this is part of a cycle. It's an iterative thing. You don't just do it once and stop and say, well, you know, work. No. You start out with something. First of all, you start out with a pretty good business understanding. Okay, what are we trying to do? What's the problem? What's the business problem we're trying to solve? Okay? And with a pretty good understanding of that, so you've got some kind of quantifiable question like to go after. And you think, well, maybe we can get data to help us answer this. Fine. Well, what kind of data do we got? And what kind of data can we get? Right? Well, there are two different questions, right? Maybe it's worth investing in your data. You talked about the availability stuff from Google, you know, they charge you for it. Maybe it's worth it, right? They're banking on it. Okay, so data understanding, and then, oh my God, yeah, data prep. Yeah, 80%, yeah, you're doing it. Sorry, you're used to it, right? And notice the arrows go back and forth over here, right? So between the business and data understanding, there's some back and forth. Like, okay, wait, we need to understand the data, we have to go back and understand the business needs better, and back and forth like that. Data prep and modeling. So you build a model, say, oh, wait a minute, we have to go and find data for this, we have to go back and, you know, reparse it or whatever, and so you spin around on that for a little bit. And then eventually, you've got your model, and you can evaluate it. see if you believe it, right? Is it a type 3 error or something? And if it's no good, well, back to the beginning, okay? That's fine, no shame in that. Like, that's how this thing works. Right? And so if you're smart, you set up your process so you can iterate in small pieces and then gradually spin it up. If it's good, then you figure out how you're going to deploy it. Put it on the website or whatever you're going to do. Okay? So let's see. Yeah, so that's, is there any connection between this data modeling, this CRISP thing, and science? Well, yeah, actually, I claim that if you look at the scientific method, it said, well, you make observations, you think of questions, hypotheses. You learned all this in the 5th grade or something, right? And forgot it 2 weeks later. And so here's how that works. Well, it turns out that this actually kind of lines up pretty well with these the macro steps in this CRISP VM. And finally, then, if you take that model and open it up, if you go to the Wikipedia page for CRISP VM, you can find the links and you can find the document that walks you through the steps. And by the way, full disclosure, it's currently promoted by IBM as part of the SPSS stuff, so but it's still good. So what do we got here? You can think of like a little dashboard, right? That says, okay, we want to use this process. What exactly has to happen? Well, we have business understanding, part 1 and 2, and do all this stuff, figure this out, cost benefits, road map, and project plan. And then, data understanding, okay, data quality, and what do we got, what does it look like, how's that? And then data prep, yeah, you got to do it. Okay, all these different ways to think about your data prep. Modeling, okay, so the part that we all want to do, fire up a Python script, that's like this little box right here, maybe a couple of these, okay? All this other stuff is, kind of to make sure when you talk to the boss, you can say, yes, it's right, I know why it's right, here's why, and you can believe it. It's a good result, right? By the way, if anybody thinks that data scientists are going out of job anytime soon, I don't think so, because I don't know too many robots that can do any of this stuff, so I could be wrong. So that's where I'll leave it. My own kind of view on the ups and downs of the machine learning world. Thank you. I know who is listening. I'll be happy to take questions. Otherwise, you can call. Okay.
Cool. Thanks, Ben. So thanks again, everyone, for coming out. I hope you enjoyed it. I'm not sure when the next one will be, hoping for November, but we might skip December and see you in January. So I'll keep you all posted. We'll communicate through meetup.com. Thanks again to Billy and Kevin for speaking tonight. And thanks to the sponsors again, Pandata, Georgios, and Jumpstart. Yeah. So, yeah, thanks, everyone. Have a good night. Yeah, definitely. Can you, Billy? Yeah.
Yeah, you.
Hold on.
Let me do. You can find Billy. Kevin, I'm going to take a picture of you, Jason, and Billy.
How you doing? Good. Yeah.
This is for you real fast.
Yeah.
Billy's.
Take a picture real quick. All right, great. Thanks very much. Relax. Thank you.
It's my first time.
Empathy. Very interesting. Give me just 1 second, please. Good job, Kevin. Oh, thanks. Okay.
Everyone.
I think it's just, I'm curious.
Yeah.
And this might just be like a whole other topic you want to try to do. How do you select your training data now? Like you said, for like blood samples or whatever, there's a small set, a small fraction of them that are actually the bad data. Or the bad blood samples, right?
Yeah.
So does that mean you can't just have like a small fraction of test data?
No,
your
you wanna-
training data, because otherwise everything's going to be skewed. Well, I'm just going to assume 90% of blood samples are all good anyway. So.
Right. So you want to have, especially in like a binary problem like that, you want to have as close to half and half as possible.
So you do have to actually nitpick all of your training data.
Yeah. And there are ways of